What if everything we thought we understood about the birth of the universe is starting to fall apart? According to several Nobel Prize-winning scientists, there's something seriously wrong with new data collected by NASA's James Webb Space Telescope, JWST. This $10 billion space observatory was designed to look deeper into the cosmic past than any instrument before it. Yet instead of reinforcing our current theories, it has delivered a shocking revelation. The universe may not work the way we believed. Within just months of becoming operational, JWST captured data that has stunned the world's leading cosmologists. Galaxies that are far too massive, luminous, and evolved to fit within our existing models of how the universe formed. Among those, sounding the alarm is Nobel laureate Adam Rees, who won the prize for discovering the accelerating expansion of the universe. He now acknowledges that these observations raise a thrilling but unsettling possibility. We may have fundamentally misunderstood the universe. The telescope's observations of the cosmic dawn, the era shortly after the Big Bang, are forcing scientists to rethink decades of established theory about the formation of cosmic structures. This nightmare data, as some have called it, is causing cosmologists to question the foundational assumptions of their field. So, what did the James Webb Space Telescope actually see that has caused such upheaval? One of its most surprising discoveries was galaxies forming just 300 million years after the Big Bang, an extremely short time in cosmic terms. Contrary to expectations, these galaxies weren't primitive or shapeless. Instead, they appeared well-formed, massive, and full of stars. According to previous models, there simply shouldn't have been enough time for such complex structures to emerge. One particularly striking example is a galaxy labeled JDES GS Z14-0, observed at a redshift of 14.3, meaning we're seeing it, as it was only 290 million years after the Big Bang. Far from being a faint smudge, it spans more than 1,600 light-years and is ablaze with star formation. One lead scientist remarked, "It is stunning that the universe can make such a galaxy in only 300 million years. But that's not all. JWST has found not just one but thousands of early galaxies that seem to break the rules. These galaxies are too evolved, exhibiting structural features that should have taken billions of years to develop. They're also too luminous, glowing with the light of billions of stars that, according to our models, should not yet exist. Even more astonishing, JWST detected organized shapes such as disk galaxies and barred spirals, indicators of maturity and stability in galactic evolution. In fact, studies show that 50–80% of these early galaxies are flat and elongated, resembling surfboards or pool noodles, rather than the irregular spherical proto-galaxies our models predicted. This suggests a level of structure and stability that should be impossible at this early stage in cosmic history. To draw a comparison, it's as if we expected to find only single-celled organisms in Earth's early oceans, but instead discovered mammals. These early findings aren't merely anomalies. They represent a profound challenge to our current cosmological model. The prevailing lambda CDM model, which assumes a universe dominated by cold dark matter and dark energy, predicts that structure formation should begin with small, chaotic protogalactic blobs that gradually merge over billions of years. That theory has stood for decades, but JWST's observations contradict it, revealing a young universe that is bold, bright, and filled with massive galaxies comparable in scale to our Milky Way, even though it's only about 5% as old. Astronomer Alison Kirkpatrick from the University of Kansas summed up the problem succinctly. Everything's too big. It's too big, too soon. This isn't a minor discrepancy. It's a deep conflict between observation and theory, so profound that she admitted to lying awake at night wondering if everything she had learned was wrong. The scope of the issue has become impossible to ignore. As reported by The Atlantic, JWST's early galaxy data plunged scientists into a reality where many long-standing theories may no longer apply. Some researchers initially wondered whether the telescope itself might be malfunctioning or if its instruments were improperly calibrated. But the equipment checked out. The data was valid. And suddenly cosmologists were facing what many now call a crisis in cosmology. a moment where observational evidence demands a fundamental reassessment of our theories. Even more surprising is the reaction from Nobel Prize-winning scientists who helped establish our current cosmological understanding. Dr. John Mather, co-recipient of the 2006 Nobel Prize in Physics for measuring the cosmic microwave background, and the senior project, scientist for JWST, was among those taken aback. He admitted that the first galaxies the telescope observed were not quite like what we thought they were. He described them as surprisingly big, bright, powerful, and numerous compared with what we expected. Coming from someone who helped measure the Big Bang's afterglow and designed JWST itself, this admission carries significant weight. Meanwhile, Adam Rees, the Nobel laureate behind the discovery of dark energy, led a JWST program aiming to resolve the so-called Hubble tension, a growing discrepancy in measurements of the universe's expansion rate. Instead of solving the issue, JWST's precision confirmed it. Rees acknowledged that these findings eliminate measurement error as a possible explanation and suggest instead that we have misunderstood the universe. In an interview with Live Science, he reflected on the possibility that we may not fully understand the universe's composition or the physics that governs it. Sir Roger Penrose, another Nobel Prize winner recognized for his work on black holes, interpreted JWST's findings through the lens of his conformal cyclic cosmology theory. This theory suggests the Big Bang wasn't a singular beginning, but one phase in an eternal cycle of universes. Penrose has proposed that the advanced galaxies observed by JWST could be remnants of a previous cosmic epoch, structures inherited from an earlier universe. While his theory remains speculative and not part of mainstream cosmology, it highlights how these anomalies are prompting even the most renowned thinkers to explore radical new ideas. What unites the reactions of these Nobel laureates is the realization that JWST is not just filling in gaps in our cosmic understanding, it's shaking the very foundations of the framework itself. Rees emphasized that these discoveries are not problems to be feared, but rather opportunities that could pave the way for a transformative leap in our understanding of the universe. But the surprises didn't stop there. JWST also intensified what many scientists already considered one of the biggest problems in modern cosmology: the Hubble tension. For years, astronomers have obtained two different values for the Hubble constant, the universe's expansion rate. Local measurements using nearby celestial objects suggest an expansion rate of about 73 kilometers per second per megaparsec. However, calculations based on the cosmic microwave background yield a lower rate of around 67. This 9% discrepancy might seem minor, but in the realm of precision cosmology, it's massive. Far beyond any acceptable margin of error. Many hoped JWST could resolve this issue by providing more accurate measurements using standard candles like Cepheid variables and supernovae, but instead of clarifying things, JWST confirmed the higher expansion rate, using its sharp vision to observe Cepheid variables that Hubble couldn't resolve. This outcome confirmed that the discrepancy is not due to measurement error. As Adam Rees put it, JWST's data deepens the mystery and points to the need for new physics. Some researchers now speculate that dark energy might be more complex than previously thought, perhaps dynamic or interacting with matter in unexpected ways. Live Science even headlined, "JWST has broken cosmology. Can it be fixed?" Interestingly, as scientists tried to make sense of the massive early galaxies, another hypothesis emerged. Could we be misinterpreting what JWST is actually seeing? A study led by Stephen Finkelstein offered a crucial insight. Some of the seemingly massive early galaxies might not be as large as initially believed. The reason? Supermassive black holes at their centers, known as quasars or active galactic nuclei, were emitting enormous amounts of energy. This intense radiation made their host galaxies appear much brighter in JWST's infrared images, tricking astronomers into overestimating their mass. When the black hole glare was accounted for, the inferred mass of several early galaxies dropped significantly, aligning them more closely with theoretical predictions. While this finding resolves some discrepancies, It opens a new mystery. Why are supermassive black holes showing up so early in the universe? How did such enormous black holes, some with millions or even billions of solar masses, form so quickly after the Big Bang? This question has now taken center stage, and even after correcting for quasar glare, JWST still observes an unexpectedly high number of early galaxies, suggesting that the pace of galaxy formation in the young universe was faster than predicted. These findings are prompting scientists to revisit several assumptions. Some are exploring whether star formation was more efficient in the early universe, or if the initial mass function, the distribution of star sizes, was skewed toward larger, more luminous stars. Others are considering more radical possibilities, such as the existence of early dark energy, a form of dark energy that briefly accelerated the universe's expansion before fading away.